Welcome back, everyone, to the last session for today. We will now be hearing about stacked garbling for disjunctive zero-knowledge proofs. This is work by David Heath and Vlad Kolesnikov from Georgia Tech, and David will be giving the talk. So over to you, David.
Thank you. Thank you for that nice introduction. Like was said, yeah, this talk is about stacked garbling for disjunctive zero-knowledge proofs, which is about using garbled circuits to construct efficient zero-knowledge proofs. This work done by myself and my advisor, Vlad Kolesnikov, and we work at Georgia Tech in Atlanta, Georgia. So some background is that in 2013, Joarek Kersman-Orlandi developed this paradigm that uses garbled circuits to construct zero-knowledge proofs. And this paradigm remains interesting today because this paradigm is efficient for proofs of very large, complicated circuits. So where the proof statement is a large circuit. This is in contrast to a lot of modern zero-knowledge research, which emphasizes fast verification time and small proof size at the cost of increasing the amount of work that the prover has to do. So for this reason, this garbled circuit thing remains very interesting. And in this work, we dramatically improve the performance of this garbled circuit for zero-knowledge paradigm by reducing the communication cost for circuits that include conditional branching. In particular, we improve conditional branching by up to the so-called branching factor. So if your circuit has B branches, for example, from if or switch statements in the underlying program, then we achieve up to factor B reduction in communication. Okay, so to motivate this, there's a couple questions. So first of all, why do we care about proofs of large statements? And then also, why do we care about proofs that include conditional branching? And so one use case that I want to show to you today addresses both of these questions. And it's about proving the existence of a bug in a code base in zero knowledge. So specifically, let's consider two players, Alice and Bob. And Alice has a public code base that she maintains. Maybe she's some company and she's hosting her code online. And Bob is a bystander who happens to take a look at this code base and notices that there's a problem in it. And specifically, maybe this problem is something that he can exploit. He can do something malicious against Alice's code base. And so maybe Bob wants to tell Alice that this is the case. He wants her to know that he can do something destructive with respect to her code base. But at the same time, he doesn't want to, point to the place in the code where the problem is, because if he did that, then she would be a long way towards being able to repair the bug in the code. And so by just saying, I know where there is a bug in your code, but I'm not going to show you where, Bob is essentially gaining leverage over Alice that maybe he can use in various ways. So this would be a pretty interesting thing to be able to do. So the way that they can do this is to essentially evaluate Alice's program as part of a zero-knowledge protocol, where the zero-knowledge protocol, the proof statement that they're evaluating essentially says, somewhere in your program, something bad goes happen. So I'll talk a bit more about what that means later in this talk. But so then they interact with the zero-knowledge protocol, and so Alice becomes convinced, indeed, there is a bug in my code base, but that's all I know. It's just, I know there is one. So next, I'd like to talk a bit about garbled circuits for zero knowledge, and in particular, talk about why this is a good fit for this problem and other problems like it, and then where there are some weaknesses that our work helps to shore up with this garbled circuit for zero knowledge paradigm. So I'm going to start by explaining how this JKO protocol works, at least at a high level, and then proceed into how we extend this with efficient conditional branching. So when you use garbled circuits to do zero knowledge, you let the verifier Alice be the so-called circuit generator. So if we recall how garbled circuits work, the idea is that Alice will choose random labels for all of the wires in her circuit. So she chooses cryptographic keys for all of the wires that correspond to semantic values that can appear in the circuit. So here I have depicted red keys as corresponding to a logical 0 and green keys corresponding to a logical 1. And later, when Bob, the prover, gets gets a version of this circuit, he will only get one of these keys per wire, and his goal was to sort of propagate the wires through the circuit, and at the end, in the zero knowledge setting, arrive at just a single green key that says, I have a witness to this proof statement. So in order to allow him to propagate this way, Alice has to encrypt an encrypted version of the logic of the circuit, and in particular, she encrypts gate by gate. So here we have an AND gate, and basically she constructs an encryption of this AND gate kind of in the obvious way, where it says, if Bob, when he gets some keys, if he has 2 green input keys, then he should be able to decrypt and receive an output key. And otherwise he will get a red key depending on his inputs. And the important point for zero knowledge is that although Bob will know all of the clear text values on all the wires, he will not be able to he will not be able to know what the encryption of the other color wire looks like. Okay. So Alice constructs these tables for each of the gates in the circuit. And so now she has this large collection of what we refer to as material. It's just this collections of encrypted truth tables. And as part of the garbled circuit protocol, she sends this stuff over to Bob. And what I want to emphasize is that this is the most expensive thing in garbled circuits, and therefore the most expensive thing in garbled circuits for zero knowledge, is just the fact that Alice has to send this stuff over the wire. And so this aspect right here is what we improve in our work, that we don't have to send as many of these encrypted truth tables over to Bob in the case of conditional branching. Okay. Right, so now Alice has sent this stuff over the wire. And so Bob also receives some input keys, which is done by oblivious transfer based on his witness to the proof statement. And now he can just step through decrypting this circuit gate by gate. And in the zero knowledge setting, he will arrive at a green key, assuming that he has a witness. The idea here is that if this is, in a zero knowledge protocol, the fact that he has a green key constitutes a proof. So again, it's the properties of garbled circuits ensure that the only way that Bob could have gotten this green key is by running the protocol as described. And then furthermore, Alice learns nothing from the fact that she receives a green key because she already knew what the green key looked like to begin with. So all she has learned is that somehow Bob was able to produce one, but not how he got it. I'll point out also that right here, I've described how to do honest verifier zero knowledge. So the protocol I've described would allow Alice to cheat. It's relatively easy to take this forward and turn it into malicious verifier zero knowledge. But I'm not going to show that for these slides because it's sort of irrelevant to what I have to talk about. But we do it for our paper. It works fine. Okay, so returning to our zero knowledge proof of bugs scenario, I want to talk about this problem in a bit more depth now, and then connect it with this JKO technique. So more precisely, what I mean by proving the existence of a bug is that I mean that somehow Bob's input to Alice's circuit will trigger some unintended behavior. So you can think of this in a clear text program as being like it tries to access an array out of bounds or divides by 0 or something like this. And so what we do is we instrument the program. We basically take Alice's program and we compile it instrumented into a circuit where the instrumentation says, if you try to, for example, index an array out of bounds, then there is a particular wire which will then be set high, right? It will say that some intended behavior has occurred. So in other words, the circuit will output 1 if and only if one of these unintended behaviors has been triggered. Okay, so now how does the zero knowledge proof of bug connect with JKO? Well, this is a really big problem. And so for this work, we considered a little bit of a simplification of the full general problem, which is what we said is that the verifier Alice will somehow split her code base into various snippets. And so what these snippets represent is they represent different pieces of functionality in her overall program. So, each one of these programs does something specific inside of her overall program. And the goal of Bob will be to prove a bug in exactly 1. Now, the point is that Bob will prove that there's a bug in 1, but he doesn't have to point to which snippet he's proving to. So the proof statement will say, one of your snippets has a bug, but I won't tell you which one it is. And then to turn this into a JKO proof, the idea is just to separately compile each of these instrumented programs into a separate circuit. And then this becomes a disjunctive proof. I want to prove to you either I can satisfy this circuit or this circuit or this circuit. Now, and then of course they can run the protocol, and then Bob can prove this fact using what I've shown you before. The problem here is that in the real world, code bases are in some sense unbounded in size. Code bases keep getting bigger and bigger. And so in reality, Alice's code base might be truly enormous. And what this means is that in this simplified view of the world, the number of snippets in Alice's code base can be arbitrarily large. And the problem is that the communication complexity of doing this proof grows linearly in the number of snippets. So this is obviously undesirable. And it's also really unsatisfying, because if you think about it, that what's actually happening when Bob proves that there's a bug in Alice's program is there is a single execution path through her program which yields a bug. So he is actually using a very small piece of her code base to demonstrate the existence of a bug, and yet she still has to simulate, construct an encryption of the entire circuit and send it over the wire to Bob. So this is the inefficiency that we take advantage of, that this disjunctive nature, there are ways to make this more efficient so that the communication complexity is much lower. Okay, so now onto our approach. So again, stacked garbling for zero knowledge is about reducing the communication cost for programs with conditional branching in this garbled circuit for zero knowledge paradigm. So traditionally, it's been assumed basically that the generator has to send enough material for each program branch separately. And this is a pretty reasonable thing to think, because it's very important that we stop the verifier from learning which branch is taken. And so the natural way to do that is just to run all of the branches and then sort of fix up which one was actually run using some sort of circuit component that selects out the correct output. So it's very, very natural to say that we have to send enough stuff for each branch. And it's this assumption that our work breaks, that there is a way to not send material for each branch separately. And in particular, we construct only enough material for the single longest branch, or in our zero knowledge proof of bug setting, enough material for the single longest snippet, right? The largest circuit, longest snippet represented as a circuit. Okay, so now I will show you basically how we extend JKO to do this. And so we need to expand our use case from one circuit to many circuits. For the purposes of these slides, we'll just look at two. But the idea is that, again, Bob is going to prove that one of these circuits, he has a witness for exactly one of these circuits. At a very high level, we're going to leverage the fact that Bob knows his witness, he knows which circuit he's going to prove, and therefore we can use this knowledge to do something a bit more clever than just sending material for all of the circuits. I also want to share two other high-level ideas that we'll use. So one is to look at this material, these encrypted truth tables, as just a string. So actually this breaks a bit from tradition, because usually the way that we think about garbled circuits is we think of them as a data structure where there's all these gates, and the garbled encrypted truth tables belong to the individual gates. And so this work is encouraging you to break from that view, and instead to view the material as something separate from the topology, and something that you can view as just a string. And in particular, what we'll see is we can take these strings and we can use bitwise XOR on them to construct aggregates, which will allow us to communicate less information. The second idea is a very simple one about using pseudo-random seeds as a compact representation of a circuit encryption. So if Alice has this circuit, she can construct an encryption of it starting from a pseudo-random seed. And if she does this, this seed is now in some sense a compact representation of this full encryption. Now, in general, we can't let Alice send this seed to Bob. That would not be secure. In particular, if we did this, what Bob could do is he could just construct the encryption and pop off the last green key and therefore forge a proof. But what we show in our work is that there are some cases where it is okay to send a seed this way. And in particular, if the seed is only used for a conditional branch which is not taken during the program, then we can represent the material for that conditional branch using just a single seed. Okay, so again, returning to our two circuits, I'm indicating here with the blue arrow that this is the circuit which Bob has a witness for, the one he wants to prove. So what we will have the verifier Alice do is, again, she'll start from a seed and she'll construct an encryption of this first circuit using one seed, and she'll construct an encryption of the second circuit using a different seed. So now she has these two collections of material. And normally what you would do at this point is you would send both of these over the wire, but that's not very efficient because, again, I'd like you to imagine not there being two of these, but there being many, many, representing the various control paths through Alice's program. So instead, what we will do is we will construct an aggregate. We will bitwise XOR these strings of material together to get something more compact. So in particular, given the material M1 and M2, we will construct M1 plus M2. Now Alice sends this material over to Bob, which is cheaper than sending the two strings separately. And from here, what we want is that Bob will somehow get the material M1 corresponding to the circuit he wants to evaluate. But we want this to happen without him receiving the seed, because again, I said that giving him the seed would be insecure. So the way that we'll do this is we'll just use oblivious transfer, where he will ask for the seed corresponding to the branch which was not taken in the course of this proof. So here he says, I want to evaluate the first circuit, so therefore I need the second seed. And now, given this information, I think it's probably quite easy to see what he needs to do. He can simply, again, using the seed as a compact representation of an encryption, he can re-expand, copying the actions of the verifier, re-expand this material M2 by just expanding the seed. And then he can use XOR to extract back out this string M1. So now we've achieved our goal, which is that the prover has access to M1, but importantly, he never saw the seed corresponding to the same circuit, and therefore he can't forge a proof on this circuit. So here, now there's these two circuits, and Bob has an encryption of the second circuit, and he has the full encryption, I should say, of the second circuit, and he has this sort of partial encryption of the first one where he only has enough information to evaluate. Again, he gets his input keys via oblivious transfer, and he steps through the circuit to get an output green key. So to complete the proof, it suffices for Bob to send green keys corresponding to all of the circuits to Alice, who is therefore convinced basically that he must have evaluated at least one of the circuits because he was only able to get seeds corresponding to B minus one of them. So this was stacked garbling for zero knowledge. Again, going back over some of the key ideas, it was about viewing circuit material, these encryptions of gates, as nothing more than strings which we can manipulate using bitwise XOR. In addition, we looked at using pseudo-random seeds as compact representations, and I showed this simple idea that you can send a seed from Alice to Bob in the case for the unevaluated conditional branches. So in our work, we showed that this yields huge improvements in terms of total wall clock time to complete one of these proofs. So what I have plotted here is on the y-axis is total wall clock time, and on the x-axis is the branching factor. So how many of these circuits are we conditionally composing? In particular, these are random circuits, which we generated, and of 2 million gates each. And so what you see is on the bottom line is our work, and the top line is this garbled circuit for zero knowledge paradigm without our improvement. And so you can see at 15 branches, we get up to a 10x improvement. So returning to our zero knowledge proof of bugs scenario, this is now great because basically in some sense, we don't care how many of these snippets Alice has in her code base because we're only going to pay communication cost corresponding to the single longest one. So as Alice's code base grows larger and larger and larger, our communication cost will stay constant, at least in this snippet scenario. And I think hopefully you can see that if we generalize from these snippets to something else, this trick will also apply based on the inherent conditional structure of Alice's code base. So this was stacked garbling for zero knowledge. Again, we improved the communication for disjunctive zero knowledge proofs for this garbled circuit for zero knowledge paradigm. And I showed one pretty exciting use case of how to make use of this improvement, which is about proving the existence of a bug in a code base. As one final experiment, we simulated 1,000 snippets ranging between 30 to 50 lines of C code, which we compiled into these instrumented circuits. And so, this is an attempt at simulating a multiple thousand line code base, 30 to 50,000 lines of code. And this entire proof takes 7 seconds for Bob to demonstrate that there's a bug in one of these 1,000 snippets on a wide area network. So this was stacked garbling for zero knowledge. Thank you. I'd be happy to take any questions.
Okay, thank you very much for a nice talk. We so far do not have any. Okay, so there's one from Thomas Schneider here. Can your idea of stacked garbling also be used for passively secure Yarrow's garbled circuit protocol where both parties provide inputs?
It can, and our improvement has been accepted to Crypto 2020, which is the generalization of this to two-party passively secure. Okay.
I have another small question. So it would seem that or is this too naive to think that you could easily generalize this to proving that I have a witness for at least this number in other words, if I want to prove that there is a bug in 3 of these 1,000 code snippets, I could also do this by using a different variant of OT in the beginning.
Yeah, so if we say you want to prove T out of N, is that what you're saying?
Yeah,
something. Yeah, so we're interested in improvements to that. There is a very straightforward way to, you do communication, T times communication, and then you can just do this. It would be nice to see if there is a way to do somehow better than that. I'm not sure if it's possible. It intuitively seems like it probably is not, but yeah, it's straightforward to get something like T out of it.
Okay, now we have another question from Dragos Rentia. What exactly is the seed role? Could you expand a bit on that? So what role does the seed play in your protocol, I guess, is the
Right. So the idea is that the seed is short, right? So in the naive version, I'll call it, the JKO paradigm before our improvement, if there were 2 branches, I had to send the full encryption of both circuits. But now with the seed, I send 1 encryption and I send 1 seed. And since the seed is much shorter than the encryption, that's a huge communication line. Hopefully that's clear enough.
Okay. Okay, good. So, good. Is this, have you implemented, is this, that must be also for here. Yeah, okay, good. So from Darius Rotaro, have you implemented a compiler for your work, transforms the high-level circuit, C++, etc., into some bytecode evaluated by your protocol? I'm not sure I can pass the sentence. But
I can say what we have done. So what we have done is that we extended the EMP toolkit. So the EMP toolkit has this little language extension to C++ is one way to think of it. And we expanded that with a notion of some things that occur in the course of zero knowledge proof of bugs, basically. So we had some array index out of bounds stuff added. But I don't think it's anything particularly exciting. It's definitely a very exciting direction to figure out how to kind of achieve the full version of this zero knowledge proof of bugs idea that I was talking about.
Okay. Okay, thanks.
Thank you.
And finally, Samuel Ranelucci asks, does this work with privacy-free garbled circuits? That's
yes, it does. It does. So that we use the state-of-the-art half gates as our underlying sort of scheme, which costs 1 ciphertext per AND gate in the privacy-free setting. So yes, it works just fine.
Okay, thanks. This was the last question we had, so thank you for that. And I guess we're sort of out of time, so I guess we'll move directly to the next speaker. If you'd like to share your screen, please.